So this lesson is going to be on annuities. And what that is a series of equal payments made at regular intervals. So in the previous question we did in the last lesson, we looked at how much money you'd have to invest now to become a millionaire in 25 years. It was somewhere around 90 something thousand. But we all don't have 90 something thousand just to throw into a savings account in a bank. Most people save up by just putting an equal amount of money at regular intervals. For example, $100 a month. Okay. Now, what we're going to look at is simple annuity, right? And simple annuity is just we're going to make our payment, our annuity payments, that match the compound period. So what do I mean by that? I mean, if you have an investment account that is, say, like in this example, 6.5% compounded yearly, well, then we're going to make regular payments yearly, right? In other examples where it's compounded monthly, we'll make regular payments monthly, right? To do it, to offset it, makes the math a lot more difficult, and we don't do that in this course. So let's look at an example then. In this example, you want to start saving your money by depositing $500 at the end of every year into an account that pays 6.5% compounded yearly. So we've done this before. Here we are, we're starting off with nothing. And so we gain no interest on nothing. And then at the end of the year, we put in $500. So then we have $500 at the end of the next year. And so we will gain 6.5% of that, which is $3,250. And then we'll also put in another $500. So now we have a total of $1,032.50. If we continue, at the end of the next year, this is what we have. Calculate the interest on that at $67.11. Then we're going to put in another $500, which would give us $1,599.61. Then we repeat. Interest calculated on this amount is this. We make another payment, and now we have $2,203.59. And we just keep going, so at the end of the fifth year, we are left with a total of $2,846.82. Okay, so in this case, the period is 1 year. And after every year, we will insert another $500. And so our new balance is always our original balance from the end of the previous year, plus the interest on that, plus our additional payment. So if we're to write this as some sort of equation, it's a little bit more complicated than our previous equation, but what we get is A, right, which is, you can think of it as amount, but we also call that, if you want, future value, which we've talked about. It's how much money we will have later. R is our regular deposits, so how much you're going to make per interval. I, we remember, it's R over N, where R is your interest rate, and N is the number of payments you make annually. And then little n would be, okay, how many payments you make per annum or per year times by how many years they're going to be. So let's look at an example, see if we can figure out what all these variables are in our example. So Steve makes deposits of $300 semi-annually into an account that pays 4% per annum or per year in interest compounded semi-annually. All right then. So A, that we don't know. that is our future value, right? It is the answer to this question. R are regular deposits. What it says is making regular deposits of $300. So R is $300. I, which is R over N. So R is our interest, but change it to a decimal. So we have 0.04 divided by how many times per year? Well, since it is semi-annually, it's going to be twice per year, which would be 0.02. And lastly, N, right? That's number of times per year, which is 2, times the number of years, which is 5. So little n is going to be 10. So now we can calculate this. So A equals, using our equation, 300 times by, got a double bracket there, 1 plus I, which is 0.02, to the power of little n, which is 10, minus 1, end our bracket, all divided by I again, which is 0.02. And if you plug all that into your calculator, you'll get 3,284.92. All right, so that's the future value. That's how much Steve will have in their account at the end of 5 years. But part B says, well, how much interest will Steve have earned? Well, to figure out that, let's first figure out how much Steve has actually deposited. So let's look at total deposit. If we don't count interest, well, Steve deposited $300 twice a year for 5 years. So a total of 10 deposits. So if we just look at the deposits, Steve deposited $3,000. So how much interest did he earn? Well, subtract the two. Looks like he earned in interest $284.92. Example number 2 says, an investor wants to retire in 25 years with $1 million. So this is kind of like our previous example, but instead of paying all at once, we're going to pay per annum, compounded annually. Okay, we're going to pay once a year. Her current investments are earning on average 12% per annum compounded annually. What regular annual deposit must she make to have the required amount at retirement? Okay, so that means A, our future value, we know what that is this time. It's $1 million. What we're trying to solve for is R, our regular payments every year. I will be R over N, which is our interest rate, which is 12%, so 0.12. And divided by 1 actually, because it says it's compounded annually, so we only do it once per year. So that's just going to be 0.12. And then small n would be 1 once per year multiplied by 25. So it's ny, which is 1 times 25, which is just 25. All right, so we have our equation, but it's going to start with our future value, 1 million, equals R, which is what we don't know, times by 1 plus 0.12 to the power of little n, which is 25, minus 1, all divided by 0.12. All right, so what we're going to want to do here is rearrange to solve for r. So first, we're going to multiply both sides by 0.12, and then we're going to divide both sides by that huge bracket so that we can isolate for r. And what we'll get is r equals, so 0.12, because we're multiplying both sides by that denominator, times 1,000,000. And then we divide by that whole bracket, which is 1 plus 0.12 to the power of 25 minus 1. We can do that. So when we punch that all into our calculator, we get r to be $7,500, which is a lot better than our previous situation of a one-time donation of $93,000. This time, $7,500 every year. All right, so our last lesson, which is still annuities, but we're going to be determining present value instead of future value. So in our previous example, when we did future value, we figured, okay, how much money do we have to put away at a regular interval so we would have, for example, $1 million when we retire. However, usually when you retire, most people don't want to just get one lump sum of $1 million, especially if you put it into an RRSP, because you'll get taxed on most of that and probably lose half of it. And then it'll be gone because you'll think you're rich, and a year later you realize you have no more money and you don't have any more money coming in every month. So this present value is what we're going to do to actually determine how much money would we want every month when we retire, for example. Okay, so if we're investing, the question could be, how much money should you invest now to receive equal payments of $5,000 per year later? Okay, or in the case of loans, if I'm making payments of $450 per month on a $20,000 car loan for 4 years at some interest rate. Okay, it's another example. So the present value of that will be the initial amount of the loan. Okay, so let's look at an example. This is a simple example you guys to do, but our equation for present value looks similar to the other equation, except we have one minus instead of plus 1, and our exponent is a negative exponent. So let's try and identify some of these variables in an example. So this says, suppose you've determined that you'll need $5,000 each year for 4 years to pay for your post-secondary tuition. Okay, well that is going to be PV or R. What do you? So in this case, it would be R, because that is going to be our regular payments that we will get every year for 4 years. So that is 5,000. Present value, that's what we don't know. It says calculate how much to invest today. Hint, today, present value. So that is present value, but we don't know it in this question. That's what we're calculating. I we know as R over N, where the interest rate is 9%, so 0.09, divided by how many times per year. It says annually, right? So we're just going to do a 1 there. And then N, right? Since it's annually, it's once a year. Okay, so that N is just 1 times by how many years you're going to be putting this money away. Now you guys are grade 11, so you got 1.5 years until you decide what you want to do after that. Let's just round that up to 2. Okay, so you have 2 years. That's not a lot of time. Hope you guys are saving. um, or maybe you're just depending on your parents. That's all right too. So does anyone have any questions? So in example number 2, okay, we're actually going to solve for something. You can solve for one on your own. Jordan has set up an annuity to help his son pay living expenses over the next 5 years. Oh, that's nice. The annuity will pay $50 per month. The first payment will be made 1 month from now. The annuity earns 7.75% per annum compounded monthly. So how much money did Jordan put in the annuity? So that's our present value. How much money did he put in right now? We don't know. We're going to have to calculate that. But it is going to make $50 regular payments, right? And I is R over N, where R is the rate, 7.75%, so 0.0775, all divided by N. Now it says compounded monthly, so that's 12 times per year. The little n would be N times Y, which is 12 times per year, times by the number of years, that's 5 years. So in 5 for the next 5 years. Okay, so let's set up our equation. So present value, how much money did Jordan put into the savings account to help out his son for the next 5 years? It's going to be 50, so R, times by 1 minus 1 plus I, which is 1 plus 0.775 over 12. Not 5, 12. All to the power of minus 12 times 5, which is 60. All divided by I once again, which is 0.0775 divided by 12. So if you plug that into a calculator, you get $2,480. So that's nice. It means Jordan put this much money into a bank account so that over the next 5 years, his son will get a payment of $50 every month to help. Okay, so how much interest belongs to this? Right? Like, how good was it that he put this in a saving account that earned interest as opposed to just, every month taking $50 out of his pocket and giving it to his son? Well, if he did every month take $50 out of his pocket, well, how much would that be? So $50 times by 12 months in a year times by 5 years, if he just took $50 out of his pocket every month, that would be $3,000. So how much money did he save by doing this investment, or how much interest did he make? Well, find the difference between these two. So your interest would be 3,000 minus 2,480, which is $520. So a fair bit. Makes it quite worth it to do it this way. So example number 3. Robin bought a bicycle for $1,500. Wow, that's way more than I would spend on a bicycle. But continuing, she arranged to make payments to the store at the end of every month for 1 year. So this is like taking out a loan, right? It could be a bicycle, it could be a car, right, for a different amount. This is a good example for us to go over. The store is charging 11% interest compounded monthly. So how much is each payment? All right, so let's go over what we know. In this case, we know what the present value is. It's $1,500. Okay, that's how much we paid right on the spot. Of course, we didn't have that money to pay, so we have a loan. The bank paid it for us. And we are going to make regular interval payments to pay back that loan, but we don't know what that is. That's just what we're going to have to figure out. Now, I is R over N, where R is the interest rate. It's 11%, so 0.11. It's kind of steep. If you get a car loan, you should definitely not get something that's 11%. If it is, say no. Divided by its monthly, so we're making 12 payments per year. And little n is n times y. So we're going to be doing this over the course of 1 year. So that's just going to be 1 times by, y is 1 and n is 12. 12 payments per year. So that's just 12. All right, so let's look at our equation. So we've got present value, which is 1,500. And that's going to equal R, which we don't know. That's going to be our monthly payments. All times by 1 minus 1 plus. And then it's I, which is 0.11 over 12 to the power of negative n, which is negative 12. And bracket, all divided by I again, which is 0.11 over 12. I'm just going to put that in brackets. So what we're going to do now is to solve for R. We are going to multiply both sides by that bracket on the denominator, and then we are going to divide both sides of this equation by that huge bracket on the numerator. So in a sense, this comes down here, and this comes up here. And then we're left with this R. And that R is going to equal this bracket, so 0.11 divided by 12 times by our 1,500, all divided by that big bracket here on the numerator, 1 minus bracket 1 plus 0.11 over 12 to the power of minus 12. And when we plug that into our calculator, we'll get something around $132.12. So you're going to be paying $132.12. Is that good or not? I mean, how much extra money beyond this $1,500 are you actually paying? Well, let's see. So how much are you paying? So we are paying that amount of money, $132.12 every month for a year. So we're going to pay this a total of 12 times, which is $1,585.44. So what we did is we paid an extra $85.44. Was it worth it? Well, it depends. If you don't have $1,500 to spend, then it's not so bad.